Number one, a train starting from rest travels from A to B with acceleration 0.20 meter per second squared, and then decelerates to rest from B to C. The total distance from A to C is 1,800 meters. The graph shows the variations with time for the speed of the train. This is the diagram. The time of travel from A to C is t, and the time from A to B is 0.80 t. Write down the speed of the train when at point B in terms of t. We can use the kinematic equation to relate the acceleration, distance, and final velocity. With this formula, if this is uh, Vb, we are going to velocity from 0 to B. So I would like to using the formula Vb equal u plus a times t. Vb is the speed of from A to B. U is the initial velocity. Initial velocity is 10, and A is acceleration, and T is time. So we can determine Vb 0 plus 0.20 times 0.80t, and the result is 0.16t. So this is the speed of the train when it reaches point B from A to B. Next question. Determine T and total distance 1,800 meters. Total distance 1,800 meters according to the information. So we can use kinematic equation to find distance. Distance equal 1/2 times Vb t squared. So we can rearrange this formula becomes t squared equal 2d divided by Vb, or t equals square root d over Vb, or t equal square root 2 times 1,000, 2 times 1,800 is 0.16, and the result is square root 20,500, and it is 150. That's the distance. Next question. Number 2. In a loop toy, a car of a mass 0.12 kilograms is released from rest. The initial point, the initial positions of the car is 45 centimeters above level ground. The radius of the circular loop is 15 centimeters. The car reaches the top of the loop at position P. Frictional and air resistance forces are negligible. This diagram shows that the speed of the car at P is 1.7 meters per second. So I will using the formula that potential energy equal kinetic energy because of the position of the car. Okay. So potential energy formula is m times g times h. So kinetic energy 1/2 times mv squared. M divided by m equal 1. So we can writing v squared equal 2g times h, or v equals square root 2gh. Can substitute the information that v equals square root 2 times 9.8 times 0.15. 1.7, 1.72 actually, but you round off becomes 1.7 meter per second. Now, determine the normal force exerted by the loop on the car at P. Using Newton's second laws in the vertical direction, if you evaluate the diagram, uh, I would like to use this rule that F and this is the for normal force plus mg equal m p squared divided by r. Okay, it's a normal force, this one, and v is the speed of the car at the top of the loop. You can see on the diagram. R is the radius. So we can rearrange this formula becomes normal force equal mv squared R minus mg. And then it is 0.12 times 1.72 squared divided by 0.15 minus m 0.12 times 9.8. And if you calculate this, the result is 1.2 Newton. State why the car stays in contact with the loop. I have provided my opinion about this. As long as the normal force is greater than zero, normal force greater than zero, the car stays in contact with the loop. Because the normal force exerted by the loop on the car at the top of the loop is still positive, and positive and non-zero. So that's why normal force greater than zero. Next question. At point A, the car collides with a block of mass 0.18 kilograms and sticks to it. After the collision, the car and the block move together with speed 1.2 meter per second. The diagram. Calculate the speed of the car just before it collides with the block. Okay. According to the diagram, we can apply this potential energy equal kinetic energy, and this is m times g times h equal 1/2 mp squared. Okay, so this is v equals square root 2gh, and then this is, if we substitute this information, is square root 2 times 9.8 times 0.45. And the result is 3.0 meter per second. Wow. Part 2. The surface from A to B is rough, and the combined car and blocks come to rest at B. The distance AB is 0.20 meters. Determine the rate of change of momentum of the combined car and block from A to B. Right, the formula is, I'd like to use this formula, FD equal 1/2 M1 plus M2 times U squared. So it becomes here F force equal D times 2 becomes M1 plus M2 U squared divided by 2D. Substitute the information. This is 0.12 plus 0.18 times 1.2 squared divided by 2 times 0.20. multiply. And if you calculate, the result is 1.08 or 1.1 newtons. So this is rate of change of momentum, or actually this is impulse. Next. Calculate the dynamic coefficients of friction between the rough surface and the combined car and block. We use the force of friction and Newton's second law, and the formula is F equal mu times M1 plus M2 times G. And if we rearrange this formula, that mu equal F over M1 plus M2 times G. So mu equal 1.08 divided 0.12, 0.18, 9.81, and the result is 0.367. Round off 0.37. Number 3, A, outlined by reference to Newton's third law how a gas in a container exerts pressure on the container walls. I have provided my answer to one. Number B, state one difference between an ideal gas and a real gas. Well, I have provided this. Number C, to containers volume 0.20 meter cube and 0.10 meters cube are filled with an ideal gas. The pressure in the larger container is 3.0 times 10 power 4 Pascal. The pressure in the smaller container is 9.0 times 10 power 4 Pascal. The temperature of the gas in both containers is the same. A thin tube with a valve joins the containers. The valve is initially closed. This is the valve. The valve is open so that gas can move from one container to the other. The temperature remains unchanged. Determine the new pressure of the gas. I would like to using this formula that P1 V1 plus P2 V2 equal P times V1 plus V2. P1 is 3.0 times 10 power 4. V1 is 0.20 plus P2 is 9.0 times 10 power 4 times 0.10 equal P times 0.20 plus 0.10. So if we calculate, this is 0.6 times 10 power 4 plus 0.9 times 10 power 4 equal P times 0.30. So if 0.6 plus 0.9 is 1.5 times 10 to the power 4, P times 0.30. So we can determine P 1.5 divided by 0.30 times 10 power 4 equal 5.0 times 10 power 4. The unit is Pascal. 4. State what is meant by a transfer wave. I have provided my answer about this. Next question. A transfer wave is traveling to the right on a string. The graph shows at one particular time the variations of the displacement y with distance x along the string. 2 points P and Q on the string have been marked. P and Q. Explain whether P or Q has the greater accelerations. I have provided one. I think this is clear. Next question. The speed of the wave is 62 meters per second. Calculate the period of the wave, giving your answer to the correct number of significant figures. First, we need to determine lambda. Okay, lambda from this point to this point is 1.2. Okay, 1.2 meters. Okay, so one wave from this point to this point is 1.2 meters. So after that, we use the formula t or time equal lambda over c, 1.20 divided by 62. And if you calculate, this is 1.936 times 10 power minus 2, or 1.9 times 10 power minus 2 second. That is time. Calculate the average speed of P during one complete oscillation. For one complete oscillation, the speed or velocity for D divided by time taken is one time taken. So it becomes 4 times distance is 0.04 meters, 1.936 times 10 power minus 2 second, and it is 8.3 meters per second. The string is now stretched between an oscillator and a fixed point. When the oscillator is set to a frequency 120 Hz, the standing wave shown in the diagram is observed on the string. It is 120 for one oscillation. So it means from this point to this point is 60. Draw the standing wave that will be observed on the same string when the oscillator is set frequency 180. 180, it means 3 times 60. 3 times 60, we need to divide, becomes 3 parts. One part is 60, so it becomes like this. Okay, you can fix by yourself for your own diagram. Okay, go on. Next. See, physicists and engineers study simple harmonic oscillations, even though most oscillations are not simple harmonic, suggest why this is a useful thing to do. I have provided my answer, this one. Okay, this is simple, SSM is simple harmonic motion. Number 5, two resistors X and Y are connected in series to a cell of electromotive force E and a negligible internal resistance. The resistance of X and Y are constant. In the circuit, the power dissipated in X is greater than that in Y. State and explain how the resistance of X compares with the resistance of Y. I have provided my explanations. One. Okay, let's continue. Great. X and Y are now connected in parallel to the same cell. This in the circuit connected parallel, just now series. State and explain which resistor has the greater power dissipations. I have provided my explanation. One. Okay. A lamp Z and a resistor R have the IV characteristics shown in the graph. Describe the variations with voltage of the resistance of Z. I have provided this, the value of VI, the graph of VI increase, so the implication, the resistance increase as well with increasing of the voltage. So when the voltage or the power or the potential difference increasing as well, resistance will be increasing. R and Z are connected in series to a cell of EMF 12 volts and negligible internal resistance. Determine using the graph the power dissipated in lamp C. Okay, so I would like to show you this graph. We're using this 50 and 50, and I 50 milliamps, 50 milliamps. If we convert to amps, becomes 0.050 amps. This one. And the potential difference 4.0 volt. So this is the current and this is the potential difference or voltage. So it means the power of Z or PZ equal I times VC, your 0.050 amps times 4.0 volt equals 0.2 watts. Let's continue. The binding energy of the stable nuclide of xenon 131 is 1.105 gigaelectron volt. Outline what is meant by binding energy. I have provided my explanation. This you may add something or you may copy this explanation. Next, calculate in gigaelectron volt per second per c square. C is speed of light, the mass of a nucleus of xenon 131. Right. I will use this rule that binding energy equal mass of separate nucleons minus mass of nucleus. Right. Binding energy is 1.105 gigaelectron volts equal mass of separate nucleus is 54 times 938. 54 because mass of protons, right? And 938 is, 54 is number of protons and 938 is mass of proton plus 177 times 940. 77 is number of neutron and then 940 is mass of a neutron. Minus is minus, mass of nucleus is mc squared, right? So it's going to be, I would like to convert into mega electron volt becomes 1105 mega electron volt because this is in mega electron volt. So it's going to be 50,652 plus 70,380 minus mc squared. Right? So mc squared equal, if you calculate this, that is 121,927 minus 1,105. and it is one. Oh, wait. If you calculate this, sorry, if you calculate, sorry, I have to write in this. The calculation, uh, this number minus 1,105, and it's equal 1,927, and this is mega electron volt, or in giga electron volt is 121.927 giga electron volt. So it means m, or mass, equal this number divided by c squared. So gonna be 121 9.927 giga electron volt c power minus 2, or per c squared. Xenon 133 and xenon 131 are two isotopes of xenon. Outline what is meant by isotope. I have provided my explanation. This, let's continue. Xenon 133 is radioactive, suggests how the binding energy per nucleon for xenon 131. I have provided my explanation about this. Compares with that of xenon 133. And this one, we compare, actually xenon 131 is stable, meaning its nucleus is tightly bound and more stable. This stability corresponds to a higher binding energy per nucleon, while xenon 133 is radioactive, meaning it undergoes decay to reach a more stable state. This lower stability indicates a lower binding energy per nucleon. Next question. Part 3. Determine the number of up quarks, U quarks, in nucleus of xenon 131. Up quarks, or U quarks, from protons equal 2 times 54 is 108. 54 because xenon 131 has 54 protons, and 77 neutron 77 because 131 minus 54. And U quarks neutrons, 1 times 77 equals 77. So the total up quarks equal 108 plus 77 equal 185 to 1. Next question. The graph shows the variations with time of the activity of a pure sample of xenon 133. Estimate the half-life of xenon 133. Okay, so to estimate the half-life, we need formula. The formula is AT equal A0 times E power minus lambda T. So we can rearrange this formula becomes E power minus lambda T equal AT divided by A0. So it means minus lambda T ln E based on ln rule equal ln AT over A0. So we can rearrange, as this is 1, ln E equal 1. So lambda equal minus 1 over T ln I would like to using this point and 2.5, this point uh, when t 2.5 days. So we are going to using 6.5. 6.5 is A 6.5. So A 2.5, A0 is 9. So it's going to be lambda equal minus 1 over T is 2.5. Okay, to learn just now 6.5 times 10 or 7. And A0 is the initial A1. This is 9. Okay, 9 times 10 power 7. So it's going to be lambda equal minus 1 over 2.5 times. If you calculate this, is the result is minus 0.3254 on, and this is the result is 0.13016 on. This is lambda. Now we can calculate the half-life of T half, the T half, T1 half equal ln 2 divided by lambda. And if you calculate the result, lambda is this one, ln 2 divided by this number, and the result is 5.32498, round off, becomes 5.3. The unit is this, the one. Calculate the activity of the sample after 25 days as a fraction of the initial activity, right? So we need to find n first, that n equal 25 or 5.3. Okay, 5.3 because of this one, 5.3, and it's equal 4.7 half life. Okay, one. And then A over A0 equals 0.5 power this number. And if you calculate, the result is 0.03847, round off 0.038. One. Describe the energy transfers taking place in a wind generator. I have provided my explanations about this. The maximum power that can be extracted from a wind generator is given by this equation. State one assumptions made in deriving these questions. I have provided also this one, my explanation. The following data are available for a wind generator. Blade rate is one, air density is one, wind speed incident of blades is one, wind speed after leaving blades is one. Determine the maximum power, stating the correct unit produced by this wind generator. Wait, sorry. Okay. So we need to find the swept area first. Area equal pi r squared. It is pi times 2.5 squared. So this is 6.25 pi. And then we use the power equations for wind turbines. P equal 1/2 times rho times A times V1 cube minus V2 cube. So 1/2 rho is 1.2. This is 6.25 pi, and V1 is 6.8 cube minus 2.6 cube. And if you calculate, the result is 3,495.86 watts, or 3,500 watts. Number 8, height of wavelength 6.0 times 10 power minus 7 meters is incident on two parallel slits. The graph shows the variations with diffraction angle theta of the intensity I of light observed on a screen far from the slits. I0 is the intensity of light on the screen due to one slit only. Question. Identify a feature of this graph that suggests that the slit width is not negligible. This is my answer. And estimate the slit width. Okay, right. We can use the formula for the diffraction minimum of a single slit. I will start from sine theta equal m times lambda over b. For the first diffraction minimum, m equal 1, the equation becomes sine theta equal m equal 1, it means 1 times lambda over b. And we can rearrange, if b, the subject, becomes b equal lambda over sine theta. Blah. So lambda is 6.0 times 10 power minus 7 over sine 0.05. Sine 0.05 sine 0.05 equal 0.05 because for small angles, sine theta equal theta. This is for the small angle. So B equals 6.0 times 10 power minus 7 over 0.05. 6 divided by 0.05 and times 10 power minus 7, the result is, this is 120 minus 7. So B equal 1.2 times 10 power minus 5 meters. Next question. Outline how the central maximum is formed. I have provided as well my explanation, explain why the intensity of the central maximum is equal to 4I0. Right. Sum of amplitudes from the two slits equal, this is the total amplitude equal A plus A equal to A. And then the intensity of wave is proportional to the square of amplitude, proportional to A squared. This is the intensity of wave. The intensity from one slit at the central maximum is I0. So we can write that I0 proportional for A squared, like that. So it means I0 proportional for uh, 2A because of the total amplitude is 2A, A squared because A squared. So it's going to be I0 proportional to 4A squared. So we can write in that total intensity equal 4A squared. A squared A squared is proportional to one to I0. So total intensity equal 4I0 like this. The spectrum of sodium contains two lines at wavelength 589.0 nanometers and 589.6 nanometers. 400 slits of a diffraction grating are illuminated. Determine whether these lines are resolved in the second order. We calculate the resolving power for the second order diffraction with uh, delta lambda equal lambda over m, and this lambda is the average wavelength. So we can determine lambda by 589.0 plus 589.6 divided by 2 because of average wavelength. So this is 589.3. Substitute into this equation, so it is 589.3 divided by m equal 2 and n is 400. 2 times 400. And if you calculate, the result is 0.737 nanometers. Wow. Next, continue. Number 9. The gravitational potential due to any isolated point mass is zero at infinity. Explain why the gravitational potential at all other points is negative. This my explanation. Sorry. By this, okay, you may copy or edit something. No problem if you have different opinion. Next, a probe is launched from the surface of a planet. It has speed 0.9 velocity escape, where velocity escape is the escape speed from the planet, v escape. State what is meant by the escape speed. This is my opinion. I will not explain that. I think that is clear. The radius of the planet is r determined in terms of r, the maximum height above the surface of the probe can reach. Right. Using rule that gravitational potential energy or GPE surface of R plus the kinetic energy of probe equal GPE at new height R. Okay, so I would like to start from the escape speed. So the escape speed or v escape, it is the root of 2gm over r. And the probe speed is v equal 0.9 times square root 2gm over r. And the kinetic energy of probe equal 1/2 kinetic energy 1/2 mv squared actually. M and v 0.9 times square root 2gm over r squared like this. So it's gonna be 1/2 m becomes 0.81 times 2gm for r divided by 1, and then 0.81, this is 0.81 gm m over r. This is uh, kinetic energy of probe. So one. And after that, we can continue. I would like to continue, right? So from this rule, from this rule, I would like to writing that minus minus Gm m. This is the GPE pressure of R. Okay, Gmm over R plus 1/2 m times 0.81 to Gm for R equal minus Gm m over R. And already simplifies one, so minus Gm m over R plus 0.81 Gmm over R minus Gm m over R. So it's going to be this minus 1 plus 0.81 Gm m, so factorize minus Gm m for R. This is minus 0.19 Gm m R equal minus Gm m R. So minus and minus becomes plus, becomes positive. And we can find that 0.19 equal R divided by R, or R equal R over 0.19, 5.263 R or 5.3 R. So this is R equal to 5.3 R. And we're going to find the height over H equal R minus R. So H equal 5.3 R minus R. It is 4.3 R. So next question, number 10. The diagram shows an ideal transformer with an iron core. A resistor R is connected to the secondary coil. So this is the primary coils, and these are the secondary coil, and this is iron core. Next, describe the functions of the iron core. I have answered this one. Okay. And next question. An alternating voltage is applied to the primary coil. Explain using Faraday's law why a voltage is induced in the secondary coil. This one. Next. The graph shows the variations with time t of the voltage V in the primary coil. The number of turns in the primary coil is 600. The peak value of the voltage in the secondary coil is 120 volt. Calculate the number of turns in the secondary coil. We use the transformer equation that V primary over V secondary equal N primary over N secondary. And according to the information that it is 40 over 120 equals 600 over N secondary. So N secondary equal 120 over 40 times 600, and it is 1,800 turns. Next. Calculate the frequency of voltage in secondary coil. Right, so we need to find first the period or t equal, we look in this graph from 2, okay, 2 to 22 here. Okay, that's one period, ms millisecond. So the period is 20 minus 2 equal 20, 22 minus 2 equal 20 millisecond or 0.02 second. So the frequency equal 1 over t equal 1 over 0.02 second equal 50 hertz. For the input voltage in part C, the average power dissipated in the resistor R is 2.5 watts. Determine the root mean square RMS current in R. So we are going to determine IRMS, root mean square current. Right. For P average, the power average is this one. This is the power average, and the peak voltage or V peak is 120 volt. This is from secondary, from potential difference on secondary, volts on secondary. Right. So V RMS we need to determine first, equal V peak over square root 2. This is the formula. And got 120 by square root 2, 84.85 volt. And the root mean square current or IRMS equal P average divided by voltage potential difference RMS, 2.5 watts divided by 84.85 volts, 0.0295 amps, round off becomes 0.029 amps. Find the resistance of R. Okay, the average power dissipated in a resistor is one. The power average is I squared RMS times R. This is the formula. So we can rearrange this formula becomes because we are going to find R. So R equal the average divided by I squared RMS. And it is 2.5 watts divided by 0.029 squared. And if you calculate, the result is 2,977.3 ohms or 3,000 ohms. Next question. Number 11. Electrons are emitted from a metal surface when very low intensity light is incident on it. This emission occurs with no observable time delay. Outline why this observation is not consistent with the wave theory of light. This is my answer. You may copy or adding something on that opinion. Light of wavelength 5.2 times 10 power minus 7 meters is incident on a metal surface and causes the emissions of electrons maximum kinetic energy 1.8 electron volt. This is the kinetic energy 1.8 electron volt. Estimate in electron volt the work functions of the metal surface. I would like to start from E photon, energy of photon equal hc divided by lambda. H is Planck constant, c is speed of light, and lambda is wavelength of light. So E photon equal here equal 6 times 0.63 times 10 power minus 34 times 3.0 times 10 power 8 divided by 5.2 times 10 power minus 7. And it's going to be 3.825 times 10 power minus 19 divided by 1.602 times 10 power minus 19. So it is 2.3876 electron volt. Now, using the photoelectric equation that kinetic energy equal E photon energy minus V. So 1.8 electron volt equals 2.13876 electron volt minus V. So V equal 2.3876 minus 1.8. It is 0.6 electron volt. So this solution. Next question. The EMF of the power supply is set at 0.60 volt. Determine the speed of the electrons as they arrive at the collecting plate. I would like to start from the kinetic energy of electrons at collecting plate is 1.8 minus 0.6. 1.8, this number from part B, the statement on part B, 1.8 electron volt minus 0.61. So it becomes 1.2 electron volt. Now, we will convert this number into joule. So the kinetic energy equal 1.2 electron volt times 1.6 times 10 power minus 19 joule per electron volt. So it becomes 1.92 times 10 power minus 19 joule. Now substitute into this formula that kinetic energy equal 1/2 mv squared. So kinetic energy is this number, 1.92 times 10 power minus 19 equal 1/2 times 9.1 times 10 power minus 31 times phi squared. Or we can rearrange this equation, becomes phi squared equal 2, because 2 times this number, 1.92 times 10 power minus 19, divided 9.1 times 10 power minus 51, it equals 0.42197 times 10 power minus 19 plus 51, 12. So phi equals square root of this number, 0.4219 times 10 power 12. And the result is 649,592.18, or we can write in 6.4959 times 10 power 5, or 6.5 times 10 power 5 meter per second.